Today we'll discuss total internal reflection, which is sort of the basic principle on which light is guided in waveguides and optical fibers, right? So it's important to refresh our understanding of total internal reflection. So again, you might have seen this in previous electromagnetism or optics courses, right? So consider reflection of plane waves at a dielectric interface, right? So let's say we have an interface. So on one side we have a medium with refractive index m1. On the other side we have a medium with refractive index m2. And then we have an incident field, incident plane wave, which makes an angle theta I with the normal to the interface. Right? So in general there will be a reflected wave and a transmitted wave, right? So this is also known as a refracted wave. Right, and then we can solve for like these angles and also the amplitudes of the electric and magnetic fields using boundary conditions at the interface. Right, so we have these boundary conditions of, for example, the parallel electric field being continuous, right? The normal displacement field being continuous, etc. So there are these four boundary conditions, right, which we use to sort of relate the parameters of the reflected and transmitted waves to those of the incident wave. Right. So this configuration that I've shown here. So here the electric field is pointing out of the board, right? Normal to the plane of incidence, right? So that configuration known as S polarization, okay, or transverse electric, which means that the electric field is transverse or normal to the plane of incidence, right? And the magnetic field lies in the plane of incidence. Right? So again, E cross H gives me the direction of the wave, propagation of the wave. Right? So there's another, or to make this explicit, I can write the electric fields for the incident, reflected and transmitted waves as pointing in the x direction, right? So the coordinate system is like this. Z is the direction in the normal, right? And x is coming out of the board, y is so the electric field is pointing in the x direction out of the board. Right, so Q can be for the incident, reflected, or transmitted. Right, so again, these boundary conditions have to be matched for all times and all points here. So the frequency of all these waves will be the same, of course. Right, and then the H we can find out by just taking K cross E, right? What we discussed last time. So there is another configuration which is known as P polarization, which is also known as TM or transverse magnetic, right? Where the roles of electric and magnetic fields are reversed, right? So there, the magnetic field is transverse to the plane of incidence, right? So there, I will write H field like this. Right, so for these two different configurations, the boundary conditions will be matched in different ways, right? And for example, when we solve for the reflection coefficients, right? So the amplitude of the electric field in the reflected wave compared to that in the incident wave, those are different for these two, right? So first thing, as you know, we get from the boundary conditions are basically Snell's laws, right? So first thing is that the angle of incidence is equal to the angle of reflection, right? Second is that this product of the refractive index times sine of the angle of incidence this n times sine theta is conserved. Right, so that this is in general true. So for both polarization. And then when we solve for the amplitudes, right? So we get these what are known as Fresnel reflection coefficients. Okay, so for the S polarization, right, S or TE. So we define this small r, the amplitude reflection coefficient, as the electric field amplitude in the reflected wave divided by the electric field amplitude in the incident wave. So we get this expression for the S polarization. This should also be familiar. So in case like this is not familiar or you've sort of forgotten this, I would encourage you to go through this again, right, match the boundary conditions and derive these conditions. And then for the P polarization, the reflection coefficient is slightly different. Okay. So again, the reflection coefficient depends on both sort of the incident angle and also the refractive indices of the two media. Okay, so our particular sort of focus is on total internal reflection, right? So that happens, as you know, when the wave goes from a denser medium to a rarer medium, right? So it goes from a medium of higher refractive index to lower refractive index. Right, so from here you can see that that means that theta t has to be greater than theta I. Right, so sort of the refracted ray is bending away from the normal compared to the incident. So yeah, for this basically the angle of the transmitted ray can be written like this from Snell's law. N1 is greater than N2, sin theta t is greater than theta I. So now as sort of this incident angle increases, this theta t also keeps increasing, but at some point basically you can reach 90 degrees, right, for the transmitted wave. So basically at some critical angle of incidence, this theta t becomes pi by 2, which means basically this transmitted ray is now like going along the interface, right? And for angles greater than the critical angle, now theta t is not or you can see basically theta t is not purely real. Okay, because basically n1 sin theta 1 or n1 by n2 sin theta I becomes greater than 1. So no real value of theta t can give me that. What does that mean? That means that there is actually no propagating transmitted wave, right, for angles greater than this critical angle. Right, and the critical angle you can see just here, so you put pi by 2 here, right? So this theta c is just sine inverse So basically what's happening for angle of incidence greater than the critical angle is, so you have a reflected wave, but there is no transmitted wave, right? And what actually happens, you recall, is there is this evanescent wave here, which is uh, sort of propagating along the interface, but the amplitude goes down exponentially away from the interface. Right, so there is this evanescent wave existing here on the other side, but there is no wave propagating into the other medium. Okay, so in this condition, I can write this cosine theta t as square root of 1 minus sine square theta t, right? And then from the Snell's law, basically I can write that as this. Now again, for angle of incidence is greater than the critical angle, this number is greater than 1, right? Which means this thing under the square root is negative, right? So this is a complex number. So I can write it like that. Right, so I put a minus sign in front of this iota here, and that is so that basically this we get an evanescent wave which is decaying exponentially with z into the other wave. Right, if you take an exponentially increasing wave which is not physical. So that's how you choose this sign. Right, so this thing under the square root now is a real number, so I can write this as some minus I beta. Okay, so now cosine theta t for angle of incidence greater than the critical angle is some purely imaginary number, right? And now I can plug this in into the reflection coefficients here. Okay, and this. So let's look at the S polarization. So n1 cos theta I. So this is a purely real number, right? Because n1 is a real number. Theta I is some angle between 0 and pi by 2. So this is a purely real number, right? So let me denote that by some alpha. Right? So I denote this not by, let me call this beta by n2. So that n2 cosine theta is now I beta. Okay, so this thing is now purely imaginary number, right? So now the reflection coefficient for the S polarization, you can see, will be like this. Right? It's a complex number, and the numerator is the conjugate of the denominator. Right? So what does this look like, right? So this means if you take the magnitude, you can see that the magnitude of the numerator and the denominator is the same, right? So the magnitude is 1 of Rs, which means in terms of power, right, 100% power is reflected.
Sir?
Yeah?
Sir, there is problem in live session actually again and again black,
Sorry, there is what?
and we have to rejoin again and again.
What's going on? Sorry. Oh,
We are not visible.
the video back?
Visible.
Okay. Especially in 10 to 15
Sir,
minutes,
And sir,
we
when
need
you
to
write
go.
on the tool, right, the things that you have wrought, we can't see.
You can't see
There is some
what?
recognition also.
Okay.
sir,
Can you
the
see?
screen keeps blacking out randomly, and then we have to rejoin, not
Rejoin.
rejoin, we have to either maximize or rejoin the screen again. Like, I don't think either the stable connection is not stable or there is something
Yeah,
else
I
wrong.
mean, I also had some issues connecting in the beginning, so that's why I got late by a few minutes. But now it seems fine from my side. Like the video is streaming. So, uh, is it visible now? Can you see the screen now?
No, sir.
Sir, the thing is that it is visible now. But the thing is that at certain interval of time, it is getting minimized, sir. Like after 1 or 2 minutes, every time you have to maximize the screen for seeing the full view, for getting the full view, sir.
Yeah, I don't know. So maybe, yeah. I mean, I guess we have no option. I just go on, and if you're missing anything, go back to the recording and uh, check out the recording, right? And then if still something is not clear, then we can discuss again in the next class. Okay.
Yes.
So I'll go on for now.
So for the
Yeah.
expression for cos theta, for the expression
Yeah.
of cos theta in the evanescent wave, it will be
Yeah.
plus I or minus I, sir.
Yeah. So I discussed that, right? So minus, why I've taken minus here is that uh, if you take minus, then if you now plug it into the electric field expression, you will get something like e to the minus some k z z, right? Which means that it's exponentially decaying in the plus z direction. If you take the plus sign, you'll actually get plus here, which means it's an actually exponentially increasing wave, which is not physical, right? That has infinite energy. So that's just convention, right? So if I took like opposite, or like if I took some minus sign here, then I have to take the opposite sign. An exponentially decaying wave into the next, into the other medium, instead of an exponential increase. Okay. Right. So yeah. So this is just uh, purely a phase, right? So magnitude is 1, and uh, yeah, there is a phase shift. And what is this phase shift? Right? It's the angle of the numerator minus the angle of the denominator. So you can see that's 2 tan inverse beta over alpha, right? If I plug in the values for alpha and beta in terms of the medium parameters, it's like this. Okay, so you can see that the phase shift depends on the incident angle, right? So above, of course, above the critical angle, I get 100% reflection with a phase shift. And that phase shift depends on the incident angle. So as I vary my incident angle above the critical angle, this phase shift is varying. Okay, so it's important to keep track of this phase shift. That, I mean, of course, you get 100% reflection, but there is a phase shift for the reflected wave compared to the incident wave. Okay, and this will be important when we discuss like waveguiding and the concept of modes.
How we got the value of alpha?
Sorry?
Sir, how we got the value of alpha? Like in this expression, in the denominator, we have put n1 cos
Yeah,
theta I.
alpha remember was just n1 cosine theta.
Okay, okay.
Right. So again, you can do the same exercise for the p polarization. Okay. and check that for the P polarization also you get. So check that for theta I greater than theta C, the magnitude of the reflection coefficient for the P polarization also becomes 1, and there is a phase shift. But the phase shift, the expression will be slightly different for the P polarization. Okay. Okay, so one way to interpret this phase shift which is happening is right, that also sort of explains why there is an evanescent wave in the other medium, right? So you might naively think that if 100% reflection is happening, then why is there anything in the other medium, right? So remember, our analysis here is for plane waves which have infinite extent, right? So actually the incident wave has infinite extent, reflected wave has infinite extent. So yes, we have an infinite extent wave coming in and going out. So that's why sort of in steady state there is something here in the other medium also, right? So instead of a plane wave, let's say if we had just a beam, right? More realistic situation like a beam with a finite cross-sectional area incident onto the interface, right? So what happens actually is, of course, you expect the beam to be reflected, right? But what happens is that this reflected beam is not exactly what to say, like it doesn't happen exactly at the place. The reflected beam doesn't start from the place where the incident beam hits the interface. Okay, there's actually a slight shift. Okay, so it's almost as if the beam goes into the other medium a little bit and then comes back out. Okay, and this shift here is known as Booth-Hanschen shift after the people who sort of first measured it. Okay, so this is a real effect. You can actually measure it in the lab. Like if you have an incident beam of finite cross section, you'll see that the reflected beam is slightly displaced, and there is a small. So you can measure a little bit of power leaking into the other beam. Okay, so if I extend this to infinite plane waves, then I get this, right? Where now basically this portion is now extended all over the interface, and I get this evanescent. Right, so basically this extra path that the beam is taking gives rise to this phase shift, right? Because when it takes that extra path, it will acquire phase. Okay, so yeah, that's sort of a recap of total internal reflection. I hope yeah, all the concepts related to that are clear. Right, so you can see why total internal reflection would be important for optical waveguiding, because you have something now which gives me 100% reflection, right? And if we talk about a guide for light, basically I want to keep it confined inside some medium and just make it propagate forward without making it leak outside, right? So this is sort of gives you a template to do that. Like any other way, for example, if you have mirrors can also reflect light, but typically the efficiency is less than 100%. Okay, it's maybe 95% or something. You might think that that's still okay, but remember, let's say I want to send a signal over long distances, right, over kilometers or something, then, and if you, at each reflection you're using 5%, then you can imagine like after 10-15 reflections, all your light is gone, right? So you actually need something which is truly 100% if you want to send light for long distances. Okay, so now you can imagine that, okay, now for a single interface I have this total internal reflection, right? So a simple way to make a guide or waveguide for light is to sort of sandwich two interfaces, right? So I have a reflection on one side. Simplest thing to do is I put another interface on the other side so that this beam is reflected now again from the other side, right? And now so it sort of remains confined in this slab in between, gets reflected and keeps moving forward, right? And since each reflection is 100%, I don't lose any light. Okay, so that's sort of the simplest way to construct an optical waveguide.
Excuse me, sir. Your video is turned off.
You gone again? Right, so let's discuss sort of some basics of optical waveguiding. Right, so as I said, the simplest guide you can have is, so you have a high refractive index medium sandwiched between two low refractive index regions. Right, so the refractive index profile looks like that. So this is n, right? Let's say this is some x, right? So this is the propagation direction z. Right, so this will have some thickness. So let's say this plane is x is equal to 0. So x equal to plus minus a are the boundaries. Right, so now if I launch some ray, right, at some angle to the axis, if it hits the interface making an angle greater than the critical angle, then it gets reflected, right? And then it will make the same angle here because these two interfaces are parallel, right? So this theta will be the same and it will just go on. Right, so the minimum angle here has to be theta c, right? So this theta has to be greater than the critical angle. So I could have, so let's say this is theta c. If I have a ray like this, right? So this angle will be smaller than the critical angle, so that will actually leak out. Okay, so those rays are not guided. Right, but rays like this, so which have a smaller angle with the axis, right, which go like that. So now here this angle is of course definitely greater than theta c. So these rays are guided, right? So you can see that there's like a cone of half angle theta c, and rays within that cone with respect to the axis are guided. Okay, so this structure, so you can see it looks like a slab, right? So So out of the board, like in the y direction, it extends infinitely in the y direction and also in the z direction, right? So it looks like a slab sandwiched between two other medium. So this thing is called a planar slab waveguide, right? If this vertical coordinate is one of the Cartesian coordinates, like let's say x, right? So this is a ray picture. You can think of this guidance as sort of like a series of lenses. So what these total internal reflections are doing is sort of countering the diffraction, right? So in the wave picture, right? So this is a ray picture. In the wave picture, basically, let's say if I have an incident beam, it will diffract, right? So it will try to spread out. But basically, periodically, what is happening is that the beam is getting refocused. Okay, so you can think of this slab as like small lenses along the length, which is countering the diffraction. Okay, I mean the analogy also becomes, I guess, clearer. So here you have a higher refractive index, and then surrounding is low refractive index, right? And for a lens also, it's thicker in the middle, right? So you can think of effectively the average refractive index in the middle is higher than at the edges, where the lens is thinner. Okay. So that looks like a convex lens and gives you a focusing effect. Some more terminology. So this region in between, which is the higher refractive index, is called core. And then the surrounding region is called cladding. Okay. And now with the same setup, instead of Cartesian coordinates, if you go to cylindrical coordinates, right, which means now this vertical axis is the radial coordinate r, right, and this is still the z coordinate, right, and then the thing coming out of the board will be like the azimuthal coordinate, which goes around in a circle. So if you go to cylindrical coordinates now, right, if you have this profile along the radial direction for the refractive index, then you can see that if I draw in 3D, it looks like this. It looks like a cylinder, right, where you have N1 up to some radius A, and then N2 after that. Right, so this is basically your optical fiber. So basically, in the Cartesian coordinate system, you have the planar slab waveguide. If you go to radial, if you go to cylindrical coordinates, you get optical fiber, right? But otherwise, basically they're the same, right? It's sort of just a coordinate system transformation. So this thing where you have a constant index in the core, right? And then suddenly in the cladding you have a lower refractive index. This is known as a step index, right? Because there is a step here at the interface. So this is known as step index either slab waveguide or fiber. Right, so you could also have varying refractive index in the core, right? So instead of a step, so for example, you could have some refractive index profile which is varying continuously, like that. This could be n of r, or for the slab waveguide n of x. Right? So it starts from some maximum value, continuously goes down to some minimum value, and then in the cladding remains at that value. So this is known as a graded index, waveguide or fiber, because the refractive index is great. So we have both types of optical fibers. Practically both types of fibers are made, and we'll see what is the properties, difference in properties between step and gradient index, and why we would want to use one with respect to the other. Okay, so another important concept with waveguides or fibers is known as numerical apertures. Or NA, might have heard. So it's basically the acceptance angle of the light incident from outside that gets guided into the structure, right? So as we discussed here, there's like a cone of light which gets guided, right? So if I'm coupling light from outside, right, so let's say I'm using some lens outside to couple light into my waveguide. Right, so there's a cone here which gets guided, right, which corresponds to a particular cone incident here, right? So there will be an acceptance cone here, so with half angle, let's say some theta NA, right? So if I have incident light outside that cone, these rays won't be guided; they'll get refracted out. Okay, so only the light incident within this cone will get guided into the, right? So that's the concept of numerical aperture. So how can we estimate that? So again, consider like the cone of light which gets guided here, right? That makes angle theta c here, right? So let's say this angle is some phi. This is 90 degrees. Right, so now here at this input interface, so this is my input. So on this side I have my fiber or waveguide, and this side like free space or air length. Right, so at this input interface I have again like this parallel reflection and refraction going on, right? So I can use Snell's law to relate this theta NA, the input incident angle, to this phi, right? The refracted angle into the guide. Right, so again, Snell's law. So on the left hand side I have air times sine theta NA. And on the other side, I have N1, the core refractive index, times sine of this angle phi, right? So you can see phi is basically 90 minus theta c, right? So I can write this as cosine of theta c. Right, and cosine of theta c I can write as square root of 1 minus sine of theta c, and you know sine theta c is n2 square, n2 by n1. Right. So if I'm coming from air, then this is just 1, the refractive index is 8, right? So you can see that sine theta Na is just square root of n1 square minus a2 square, right? And this is usually referred to as the numerical aperture. Okay, so if we take some typical values, so let's say n1, so optical fibers are made out of glass, right? So they will have a refractive index between, let's say, 1.45 to 1.5 in that range, depending on which type of glass and what type of doping it has. So typically, N1 and N2 are close to each other, not very different. And we'll see the reasons for that. Right, so if, let's say N1 is 1.48, N2 is 1.46, then the Na comes out to be about 0.24, which corresponds to an acceptance angle or half acceptance angle of about 14 degrees. Okay, so if I have a lens which focuses light to an angle, like cone of half angle 14 degrees, then all of that light can be guided into the right. So if you want to increase the acceptance angle, right? So if I want to collect more light like this, you can see that the difference between N1 and N2 should be larger, right? So if the index contrast between the coherent cladding is larger, then you have a higher Na, and acceptance angle is more, right? So this is an important parameter, especially if, for example, coupling light into my fiber or guide, right? So let's say, so typically you have light coming out of a laser or LED or something, right? It's coming out in free space and you want to couple it to fiber. So what kind of lens should I use, right? So naively, you might have thought that, okay, I have this fiber here, tiny fiber, right? My light is coming. So the bigger lens that I use, right, which means a lens which can focus light to bigger and bigger angles, right? So for example, you can also define an Na for the lens, right, which is also defined in the same way. So depending on the focus and the aperture, focal length and the aperture of the lens, you define this Na for the lens, which is basically if you have a collimated parallel beam coming in, what is the cone that angle that the cone makes when it focuses light, right? So basically, what you want to do is that the lens Na should be smaller than the fiber Na, right? Because so there is some Na for the fiber, which is like an acceptance cone with where all the light is coupled into the fiber. Anything outside that will not be coupled into the fiber and it will be lost, right? So if the lens has a higher Na than the fiber, then a lot of light will be lost, right? So basically, you want to use a lens which has equal or slightly smaller Na than the fiber to couple light efficiently into the fiber. Okay, so basically you want to use low Na lenses, which is sort of counterintuitive, because typically, like for imaging small things like in microscopy or in biological imaging or something, people use very high Na lenses. Okay? So almost Na like 0.8, 0.9, where you're collecting almost all angles up to almost 40, okay? Because you want to collect maximum light. But for coupling here, actually that's not the case, right? You want sort of low Na.
Sir, we
so this
prefer high.
Sorry, yeah.
Sir, we prefer high Na lenses or low Na lenses.
Right. So if you want to couple into fiber, then you want a low Na lens, right? You want a lens which has Na lower than the Na of the fiber, right? And we saw that typical Na of fiber, let's say, is 0.24 or something. So this is also for a multi-mode fiber. Okay. We'll discuss the concept of modes later, but we are using this ray analysis. Okay. This ray picture, as you know, the geometrical optics picture is only an approximation, right? The true picture is the wave picture, where we actually solve for the fields using Maxwell's equation, right? So this ray picture is valid when the fiber is highly multimode, okay? Which means basically that in the mode picture, it's supporting a lot of modes, okay? We'll discuss what modes are exactly later, but in the end, what I'm trying to say is that typically fibers are very small in. Okay, so this 0.24 is for highly multimode fiber, which is sort of the upper end. Okay. Nowadays, we mostly use single mode fibers or few mode fibers, which will have even smaller end. Okay, so they'll have like 0.1 or something. So now, if you want to couple efficiently from free space, you want to use a lens which has actually smaller NA than that, right? Because only the rays which are within the cone of the acceptance angle of the NA of the fiber will get coupled, right? The rest of the rays will get lost. So for example, if you have a fiber of NA 0.2, you're using a lens here of NA 0.6. Most of the light that is focused by the lens will not get coupled into the fiber, right? Because the angles of the rays coming are at very steep angles, which don't get coupled into the fiber. Is that clear? Another way to see is that the rays which are guiding here are mostly making very small angles, right? Especially if this index contrast is small, N1 and N2 are close, then you can see that the critical angle is very high, right? It's almost like 90. So these rays are very like almost along the axis, making a very small angle, right? Which means that rays coming from outside also have to make a small angle. They can't make a very large angle because they won't get refracted so much. Right? Like this is in contrast to, as I said, if you're doing some microscopy or imaging of some small biological samples or something, there what you want to do is something is emitting and you want to collect as much light as possible, right? So there, like you have some point source kind of thing emitting light, sort of in all direction, and you want to collect as much as possible, right? So there you want to use a very high NA lens, which can collect a cone of very large angle, right? And then I can collect all the light in image. Right. So as I said, this ray analysis, what we've done so far, is valid for what is known as for multi-mode fibers or highly multi-mode fibers. So what do you mean by that, right? So you can see there are some dimensions here, right? So as I said, the size of the core is A, right? So in a fiber, so that for example, if this is a radial coordinate, if this represents an optical fiber, then this is just the radius of the core, right? A. Or if it's a slab, then it's like a half thickness of the slab, right? So there is something called a V number, which is defined. Okay, so that depends on the size of the core and this numerical aperture, N1 square minus N2 square, and the wavelength. Okay. So if this V number is large, so typically if it's more than 10 or something, then this ray picture is sort of valid. The approximation is good. But if your V number is low, like below 10 for example, then this ray picture is actually not sufficient, right? Then you have to go to the actual wave picture, which you will do, right? Solving Maxwell's equations and solving for the field profiles in the wave. Okay, so this V number roughly gives you the number of modes which are guided. Okay, so you can see that it depends on this numerical aperture, right? So the index contrast. So if the index contrast is higher, N1 and N2, then this V number is higher, and you guide more number of modes. Or for a given N1 and N2, this A over lambda, right? So the size of the core compared to the wavelength. If that is big, then this V number is large, right? And you have a multimode fiber, right? So typically, like for telecommunication wavelengths that we use optical fibers, right? That's near in the near infrared, right? So let's say this is 1.5 micron. Right. If you have a multimode fiber like with these values and let's say the radius of the core is like 25 micron or something, right? More than much bigger than like 10 times the wavelength, then this ray picture is valid. Okay. But as I said, nowadays, especially if you look at the optical fiber network which is laid down for telecommunications, we mostly use single mode fibers, where this V number is actually close to 2. Okay. So in that case, this analysis is not valid at all, right? We just have to go to the wave picture. Right. So to make the fiber single moded, what is done is, so first N1 and N2 are made very, very close, even closer than this. Okay. And then A is also made smaller. So typical, like if you look at commercial single mode fiber available today, sort of the core radius is about, let's say 5 micron, 10 to the minus 3 or something. Okay. And so why do we need fibers with low V number or supporting only a single mode or few modes compared to fibers with lots of modes that we'll discuss soon. Okay, so yeah, we'll stop here today. And so next class we'll discuss another important property of optical fibers, which is basically just propagation loss or attenuation, right? So as I said, ideally, if you have a perfect dielectric and the light is composed of photons which have energy less than the band gap of the dielectric, then you would expect there to be no loss, right? And but that's not the case, right? Although optical fibers have extremely low loss, but they have some finite loss. So we'll see where that loss comes from, what are the typical values, etc.